Hello everyone, welcome to this video on field theory. In this video we are going to see examples of fields. So let us look at this set F, which is given to be non-negative even integers, right? We need to determine whether this is a field or not under the operations of addition and multiplication, right? So let us get started. The first thing that in the last video we have seen various properties or axioms of the field necessary for a set to be a field. So let us first check the distributive property. What is that? If I take any three numbers A, B, C from the set F, then this property should hold. A star B plus C, this should be equal to A dot B plus A dot C. So let us look at this property taking any two arbitrary elements. So let me take 2 and B as 4 and C as 6, right? So this should be equal to 2.4 plus 2.6. So here I have 2.10. So this would ultimately be 20, and from this side I have 8 plus 12, so this is also equal to 20. So these two are equal. That means the distributive property holds for this set with the given two operations. Now let us look at the closure property with respect to addition. Let us first see that. What is that? If I take any two elements AB from the set F, then adding these two, then they should again belongs to the set F. Now you can see that the set F contains all even non-negative even integers, right? So if I add these two, I'll again get an even integer. So obviously this belongs to the set F. So closure property under addition holds. Next we can see that we need to check closure property under multiplication, right? So what is that? If I take any two numbers A and B from this set F, then A dot B should belongs to this set. So if I take any two even numbers and I multiply these two, they'll again be even numbers. So this property also holds. Now let us look at commutative property under addition. What is that? For any two numbers A and B in the set F, A plus B should be equal to B plus A. For simple numbers, this thing is true. So this property is also satisfied. Moreover, for multiplication, the property should be A dot B should be equal to B dot A. Also, this is true for numbers of such kind. So there is no problem in that. Commutativity is also valid. Closure is also valid. Distributive property is also valid, right? So now let us look at the associative property. What is that? If I take any three numbers A, B, C from the set, associativity under addition says that A plus B plus C should be equal to A plus B plus C, right? So this is also true for such kind of numbers. You may check. There is no, you cannot find any number in the set which violate this. So this property is also satisfied. Moreover, under multiplication, what is that? A dot B dot C, this is equal to A dot B dot C. So this property is also true, right? For numbers, any numbers in the set F, suppose I have 2, here I have 4, here I have 6, right? And here I have 2, 4 and 6. So this should be equal. You can check this easily. 2 into 24, and here I have 8 into 6. So I have 48 is equal to 48. So this property holds for every number. You may check this. So now let us move on to checking the existence of identity both in case of addition and in case of multiplication. So if I have any number A in the field, so what should I add to this so that I get A again? And this number should be in the set. So clearly you should add 0, then obviously you will obtain A. So let us see if 0 belongs to the set. Yes, it does. So we have our additive identity with us, 0 as the additive identity. Moreover, now let us look at the multiplicative identity. What should I multiply with A so that I get A again? So it should be 1. But does this 1 belongs to our set F? No, it doesn't. So we say that there is no multiplicative identity present in the set. So from here as this one property is not satisfied, so the set F together with this operations plus and dot is not a field, right? So this is not a field. So what if I add 1 onto this? I create a new set F which is equal to 0, 1, 2, 4, 6 and so on. Then the set F together with these two properties is a field. Until now it is, yes. So with the new set, let me call this as F1. So F1 until here, F1 has multiplicative identity as 1, right? So let us check now the last properties, that are there any numbers which are inverse to the given numbers in the set. So if I take A belongs to the set F, so for additive inverse I should have some number here so that I obtain 0. So this number should be minus A. So that means for every number here in the set I should have a negative of these numbers. So for 2 I should have minus 2, for 4 I should have minus 4, but these are not present in the set. So this property is not satisfied. So I can say that there are no inverses presently. So the set F1 is also not a field, right? Now what if I say that I create another set F2 which contains all the negative numbers also, like dash dash dash. Then I have minus 6, minus 4, minus 2, then 0, then 1. Then I should have minus 1 also. Minus 1, 0, 1, 2, 4, 6 and so on, right? So this set together with the operations F2 together with the operations of addition and multiplication now satisfies these properties. Now let us check for the existence of inverse multiplicative inverses, right, under multiplication. So if I have some number A, then what should I multiply to this number so that I obtain the multiplicative inverse? So multiplicative identity, what is that? That is 1. So what should I write over here? I should write 1 upon A. So this 1 upon A should be there in our set F. But is it so? If I take the number A to be 4, then 1 upon A is equal to 1 upon 4 should be there in F. But this is not the case. So F2 is not a field, right? So what should we do so that we make it a field? We construct another set. What is that? Now it contains all the rational numbers as well, in addition to those. So in addition to F2, right? So now this property is also satisfied. That means for every number we have the additive and as well as multiplicative inverses. So we say that this set is a field. And if you see closely, what is this set? This set is the set of rational numbers. So the set of rational numbers denoted by Q together with the operation of addition and multiplication forms a field, right? This forms a field. So now let us move on and look on to another example. If I take the set F to be the set of integers and the operations I define to be addition and multiplication. Now whether this is a field or not, you need to check this. You can pause the video and check whether this is a field or not. No, it is not a field. Why? Because in this, if you the field of integers, you have multiplicative identity. What is that? It is something of this form: infinite set, -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, and so on, right? This is the set of integers. So this set has the multiplicative identity. What is that? That is 1. It has additive identity. What is that? It is 0. It has multiplicative inverses. Sorry, it doesn't have multiplicative inverse, because if you take an element as 3, the inverse should be 1 upon 3, which does not belongs to the set of integers. It has additive identity. If you take a is equal to 3, then -3 belongs to the set this, right? So there is no multiplicative identity. So this set together with these operations does not form a field. So this does not form a field, right? Moreover, on the similar grounds, we can say that the set of real numbers and the set C of complex numbers, they both are fields under the operation of addition and multiplication. This is an exercise for you to check whether they are fields or not. Exercise: check whether R together with addition and multiplication and C together with addition and multiplication are field or not. I told you they are field, but still I recommend you to check these every property so that you are habituated to these kind of things, right? So thank you for watching the video. I'll see you in the next video with more examples.